I think we're going to get started. Before Artem is going to introduce our speaker. But first, I just want to welcome everybody as kind of a joint astrobiology astronomy colloquium. We've been going kind of waffling back and forth between having independent colloquia or seating ourselves within all of the different departments that contribute to astrobiology. So here we're doing the latter. Last quarter we did the former, and but so thank you to astronomy for allowing us to do that. And I want to say a special thank you to Olivier for coming. He is the director of an Astrobiology Institute in Marseille, and it's been very interesting to talk to him about all the ways that he is trying to get people together to have interdisciplinarity and to learn the language that everybody speaks. We also had a great discussion about creating academic programs in astrobiology, and I just want to give a shout out to the 4 students here in the middle who took the undergrad astrobiology class last quarter and decided to switch to astrophysics. So you can see that there's a demand. All right, I'll turn it over to Artem.
Thank you so much, Natalie. Thank you everyone for being here. And so it is my pleasure to introduce Olivier Mousis, who is a professor of astronomy and astrophysics at the Laboratoire d'Astrophysique de Marseille at Aix-Marseille University. And so Olivier works on the links between the physical and chemical properties of planetary bodies and the formation processes and evolution. And he was also very involved in the design and of robotic missions, especially in the solar system. He was a PI of a few proposed missions like probes to Saturn or orbiter to Enceladus, the mission Moonraker. And yes, as Natalie said, he's the director of the Institut Origine, which is a Astrobiology Institute in Marseille, at Aix-Marseille University. And as a personal note, I just want to say that apart from being an amazing scientist, Olivier has also been a wonderful human being, and that is from someone who has spent 3 years of his PhD supervised by Olivier. And so it's my pleasure to have him here to give you a talk.
Thank you, Artem. Very nice. So thank you, Natalie. Thank you, Artem, and thank you, everyone, for welcoming me here. It's a pleasure to be here in Santa Cruz. And I should have prepared some slides about my institute, but I think it's too late. The next time.
We can ask you a question.
Yeah, of course. So the purpose of my talk of the day is to discuss about the origins of the Galilean moons in the context of the future missions. So the Lisa Juice mission has been launched almost 1 year ago, and you know that the europa-clipper mission will be launched this year if everything goes well. So those 2 missions will arrive in the Jovian system at the end of the 20s, between 29 and 30, and they will provide a big amount of data. So we need now to prepare those missions in terms of how using those data to optimize the scientific return. So that's why I converted myself. I went back to the moons because during a long time I did plenty of other things. But now in the next decade, I will progressively go back to the moons investigations. So here I present a few tips I've done in the past and or recently about the origin of the moons. So my discussion of the day, my talk is divided in 4 different parts. The first part, I will discuss the different structures, the different proposed structures in literature about the Jovian circumplanetary disk. So you usually say CPD because it's easier to pronounce than the circumplanetary disk. So keep in mind this is the word CPD. After that, I will discuss the composition of markers that can be used to assess the different moon formation scenarios. Those markers will be provided by the 2 missions, JUICE and Clipper. That's why it's interesting to prepare in advance what can be derived for those future observations. After that, thanks to the genome mission, I will derive a link between the formation of Jupiter and that of the Galilean moons, because you cannot discuss the origin of the moons without discussing the origin of Jupiter. Those 2 things are really connected. We need to consider the Jovian system as a whole system. Considering the moon themselves alone, it's a mistake. So we need to consider the whole system. And at the end, I will just give you an overview of what I did with students recently about the formation of organic matter and the photosolar nebula. And organic matter, there are plenty of astrobiologists here. You know that it is very important. But we start to realize that organic matter is needed to explain the properties of the moon. For example, there is a recent paper which argues that to explain the density of Titan and other minor planets, organic matter must be accreted by the body. The problem is that organic matter is very fragile, so how can it survive up to the formation of the moon? So we'll discuss this point later. Anyway, let me discuss first the different structures of the Julian CPD, which have been proposed in the literature. And the first point is the fact that there is a very specific property of the Galilean moons. It is their density gradient. Because if you go away from Jupiter, you have Io, Europa, Ganymede, and Calypso. And something is strange is the fact that Io is almost dry, Europa has about 10% of water, and Ganymede and Calypso, they are half made of water. So you see this gradient. It's very strange. And this gradient in the Jovian moon system is not the only one in our neighborhood. If you go around other stars, similar gradients have been observed. For example, the TRAPPIST-1 system. The inner planets are dry, the outer planets are wet. So when I say wet and dry, it's just based on the density measurement. Okay, those measurements in the Galilean moons are very precise. So yes, they can be used to precisely derive the fraction of volatiles inside. So any model proposing a formation scenario of the moons must be consistent with this feature. It does decades and decades that we know this feature, and it's not easy to explain the density of the moons during their formation in a single strike. There are specific models which will explain, for example, Europa, but they are not consistent with the other densities measured in the other moons. That's why we need to have an overview of the moon's formation. We need to explain the origin, keeping in mind this density gradient. In the literature, the good thing is that we have ideas about the moon formation, but it's still an open field, and it's less crowded than the exoplanet field. There are plenty of scientists in the exoplanets, but in moon formation, moon evolution, there are not that many scientists, and it is a very warm topic as well. It's very interesting. So in the past, there were several scenarios which have been proposed in the literature. One classical scenario is the one which has been proposed initially by Caleb and Moore. In this scenario, the author assumes that the building blocks of the moons come from the PSN, the Protosolar Nebula, and they were created in a very cold environment. So the building blocks of the moons, they formed around Jupiter itself. Another alternative scenario, which is consistent with the first one, is the fact that the building blocks of the moons, they also originate from the PSN, the Protosolar Nebula, but they have been progressively devolatilized during their migration within the CPD. Why? Because the CPD, there is a thermal gradient. The inner zone is warmer than the outer zones. So when you have a building blocks, a pebble, planetesimals, which migrate inward, it experiences progressively a heating. So if your planetesimals are small, in the form of pebbles, they lose their volatiles. And this scenario can explain why the outer moons are ice-rich and why the inner moons are volatile-free.
Can I ask you a quick question?
Sure.
I'm not a planetary astronomer, so I'm surprised, is migration already going on at this point? I thought it was later.
It's easier to migrate a dust compared with a big planetesimal. Yeah, because the dust is coupled with gas, so it's evolving to the gas. The big planetesimals are really other interactions, but it's not so easy.
So migration is important.
Yes, yes, and it's part of the puzzle. But anyway, there are some scenarios which advocate the moon formation at their current place. Okay. So this classical scenario was discovered during decades, the original idea of Cruz and in 1991. But it's not today. I think that it's worth to be considered. What is the basic idea? The basic idea is that the Jovian CPD was extremely warm and hot and dense. So any building blocks from the PSN entering the CPD was initially vaporized because the CPD was extremely warm. So it is during the cooling of the CPD that the building blocks of the moons condensed again and were created by the forming moons. It is exactly what was proposed by the Cruz and in 1981. And this idea, I said, during decades, we forgot this idea, but now there are some CPD models which show that the temperature of the disk was extremely warm. So that's a possible option. Last idea, so Francis, sorry, I made a mistake with the name. So it's Carver is the first name of Carver person. I just realized that now. So it's a paper. It is an idea developed by Carver person and Francis here. So it is the idea that the moons are created with their current isotope ratio, but because of greenhouse effect, the hydrosphere is very warm and it is in vapor phase, and there was some hydrodynamic escape, and some moons could lose their hydrosphere thanks to this escape. And it could explain the origin of Europa. And so, in fact, this scenario could be completely with the other. So that's interesting because it does not happen at the same time of moon formation. This scenario is rather post-formation scenario. So anyway, so let's go back to the different structure of the disk. So here I show you a SPH simulation, which shows that during the formation of Jupiter, you have streams of gas and gas-coupled solids entering into Jupiter. So they are created by Jupiter. And during this accretion, you have really a structure of disk which is found around the giant planet, the forming giant planet. So the CPD appears at the very end of the giant planet formation. Oh, another thing. My PhD, I did it on the formation of Titan. So at that time, I was working on the CPD models, but it is only since 2 or 3 years that we observed for the first time a CPD around another planet. It was due to VLT observations. So it's incredible because it is the first time we saw that, this disk around another planet. And the shape of the disk is exactly the one which was predicted by models. So there is a Hill radius, which corresponds to the upper limit of the size of the disk. And it is exactly what was observed around giant planets. The size of the disk was the one which was simulated by our model. So that's interesting. But okay, the thing is that during several decades, I've been working on that without knowing if it exists or not. So that's incredible. Because those who work on exoplanets, they know they are there. But working on CPD models without knowing it could exist, it's another topic. So anyway, in this classical approach, what we have is that we have a CPD forming around Jupiter. You have a centrifugal radius. So at this point, the gas here is expanding outward, and here it's moving inward. And the solids, which are created by the gas, they come from the top layers and they go to the mid plane, and they are created here and they form the embryos and the moons. So this classical view, it's taken from Robin Callop and Bill Ward. And in this case, the embryo which form here, they undergo type 1 and type 2 migration, and they move inward, and they are halted by a resonance chain. So that's why the Galilean moons are all in resonance. Once they get this resonance, they stabilize. Another scenario, so the one I showed here, it is an accretion disk. The one, it is a paper by Badidin and Morbidelli, a revelation paper, in which they assume that it's not an accretion disk, it's a decretion disk. The stream of matter comes very close to Jupiter, and the gas and the solids, they move outward instead of going inward. So in this case, there are some advantages with this scenario. Among those advantages is the fact that the disk is already supersolar, and the formation of the building blocks of the moons is faster than the other model. Honestly, the only weak point is that there is no evidence for such a scenario. We don't know if it could exist. The classical view is the accretion disk. So accretion disk, decretion disk. After the disk can be cold or warm. So here it is a cold CPD model. It's based on the prescription of Callop and Ward. So the accretion rate of the gas and gas coupled solids is very slow, very slow. And because it is a very slow accretion rate, the temperature of the disk is cold, almost cold. The temperature of the disk typically is it's between 400 and 150 K at the moon location. So this classical model has been used by plenty of authors. It is a classical use, a canonical model in which the temperature of the disk progressively increases when you move inward. And so IO is at about 400 K, and that could explain why the IO is volatile free, because building blocks of IO would have been devolatilized. So what I will say is this model, as any other model, it's an ad hoc prescription, because the temperature profile is tuned to the current location of the moon. So it is a weakness of this kind of model. It's not based on it's tuned like any model. That's the problem. Another kind of model, it is a hot CPD model. So it's based on the work on Judith Sulaki. And those models, so she limits the variant of the Jupiter formation. At the variant of Jupiter formation, the accretion rate on the CPD is very high, and the temperature of the disk is very, very warm. According to our model, it can go up to 13,000 K. It's very important. It's huge. It's not correct because there is no opacity law going up to this temperature. But anyway, it's at minimum a few thousand K. So that's why now I recognize that the model of predictive lake is valid in this kind of model because they reach the temperature which is high enough to vaporize any solids coming from the PSN. That's interesting. But anyway, everything is connected. Formation time scale is key because if you form your moons very early during the disk lifetime, at that time, at this epoch of the disk, of the CPD, the accretion rate will be very high, and the CPD is very massive and warm and hot, dense. If the moons form late within the CPD, the accretion rate in the CPD will be very low. At that time, the CPD has a very low mass, and it becomes cold. So during its evolution, the CPD around Jupiter evolved from very dense, very high temperature to very low temperature. So forming the question is, when did you form your moons? Is it early? In this case, the disk is chemically active. Did you form your moons very late? In this case, the disk was so cold that there was no chemistry in the disk. That's the open question.
So what is the source of the heat?
Here,
Just gravitational.
it's just the luminosity of Jupiter. It is also the turbulence, which is a source of heating of the disk. There is a high accretion rate creates a lot of dissipation. So the other question, what is the source of turbulence? So there are specialists of turbulence. We still don't know. There are plenty of mechanisms which are proposed in the literature. So turbulence, the range of turbulence is still an open question. It can be magnetism, it can be plenty of things. So the question is the time scale formation. When the moon is formed, is it early or late? And depending on this time scale, everything is changing. So thanks to the JUICE and europa-clipper missions, we try to address this question because depending on the formation time scale, the composition of the moons will be completely different. So that's why we need to send those missions. Let me show you a model which is currently under construction with Antoine Cheverger, who is working with me as a PhD student. So we decided to work on the 2D CPD model because there are not that many disks of this kind. And so what we have here in the 2D CPD model, we have an optically thick region, and outside we have an optically thin region. And so what happens, because the region is optically thick, there is self-shadowing of the Jovian light, the Jovian thermal emission. And so what can happen here? You can have here a very far region outside the zone, and a bit further, the temperature goes back to very high value. So we can have core regions surrounded by warm regions. So that's interesting. It is what we are doing. So it's a paper under preparation. And then can show you a few slides. Artem, I think I gave you the wrong presentation. Or I made a mistake. Sorry, it's my fault. I was not supposed to show you this slide because I gave a talk recently and I realized that I wanted to show the cold region, and it's here. It's cold. Yeah, it's here. It's here. But I prepared I didn't prepare another figure because the cold region was not easy to find. So it's my fault. So anyway, sorry. So trust me, during the evolution of the disk, it is a temperature. It is a temperature map of the disk. There is a cold region which appears during the first 100,000 years. So it has implications for the moon formation because typically moon formation can take a few 100,000 years. So if you can form a moon in these cold regions. So that's very interesting. You can form a moon in the hot region, in the inner and warm region, in the outer and warm region, and forming a colder one in the middle. Yes, typically what we see here, it is a depletion of the disk as a function of time. And you see that after 300 kiloyears, the mass of the disk has depleted by a factor of 100 million. So we need to form the moons very quickly. Over a few thousand years, this kind of model. Moon must be formed fast. That's an outcome of this kind of model, assuming the material comes from the disk itself. So it's an ongoing work. So we are writing a paper on this topic. So let me show you what can be the compositional markers to assess the different moon formation scenarios. One key observation marker is deuterium, D2H. Are there some people here who are familiar with the deuterium chemistry? So deuterium. So you know that deuterium is a main isotope of hydrogen, which has been built by the Big Bang. So the sun value is the one which has been synthesized by the Big Bang. Okay. So as you know, we are all made by 70% of water in your bodies. Okay. And what's interesting is that the value here in your bodies is homogeneous. So the value if I measure the D2H in your body, it corresponds to the small standard mean ocean water. The D2H value in your body is similar to the value in the clouds, in the oceans, in the rivers, whatever from where you are. We are all homogeneous. It's another testimonial of the fact that we are all similar. So we have all the same D2H value. And so when we try to infer the origin of water on Earth, we compare the D2H value on Earth with the values of comets, if we want to see if those comets contributed to their value. So here, what you see here, the blue value, the blue bar, the blue line corresponds to the bulk Earth value. The value in your body, it's about 1.5 10 to the minus 4. And here you see the cometary value, which is here. So you can see that comets have a D2H ratio which is close to the Earth, RT2. Churyumov-Gerasimenko is higher. And you have here Halley comet, Halley-Bopp, and Yakutaki. So clearly, we can derive that comets probably contributed to the Earth value, but it was not the only reservoir. This is what we can say. I can tell you a secret, please don't tell that to anyone. So we just realized with my colleague Katimant the D2H value in 67p, and we find, thanks to her work, we find that the value in 67p should be revised down, and now it is consistent with the Earth value. It's a better a few days ago. So what does it mean? It means that a short period comet like 67p will have contributed to the Earth value. So it's a relevant question. Okay, but there are some missing pieces. I'm thinking about the origin of water. There are missing parts of the puzzles. Today we have no measurement in asteroids. So I would bet my hand that the asteroid value is similar to the Earth. Because so the origin of water on Earth is still an open question. Was the water accreting with the Earth during its formation? Because you know what is the fraction of water on Earth. What is the fraction of water on Earth? I don't speak to the planetary astronomers. So who can tell me the value? What did you learn in your course? Let's take someone from who adaptive optics, for example. So the French. So what is the value, the fraction of water on Earth? 9 years. You have an idea. So you have a number in mind. Please take the risk. What do you think? What is the
1%.
Sorry?
1%.
1%? Are you sure?
Okay.
So who can say better? Is there a better number here? You want to say something?
I'm just wondering, are we betting on fresh water or just water in general?
Water in general.
75%?
Whoa! Oh. So what you say is just the fraction of the occupied by water on the Earth's surface. So you think in terms of surface fraction. But the bulk abundance of water on Earth, it's about 10 to the minus 4. So 0.01%. So yes, it's very low. But for an astronomer, it's zero. You know, 0.01%. So now that's important because this very small amount of water on Earth, it allows the development of life. But trying to argue, to explain where this 0.01% comes from, it's a nightmare. It's so small. So you can accurate that during the Earth's formation because that water can be absorbed on rocky grains. Water vapor can be absorbed by the rocky pebbles. It can be a late contribution by comets, by asteroids, by a mixture of comets and asteroids. So that's still an open question. But that's today we are in 24. We are made of 70% of water, and we still don't know from where it comes from. So that's something insane, I think. So anyway, so this work is interesting. This figure is interesting. It's taken from the paper by Roger Clark and colleagues. Usually, you need almost in situ measurement to measure the D2H in planetary bodies. So, for example, in the Halley Comet and it has been made by mass spectrometers. We can use radio wavelength also to measure the D2H, the gas phase, so that's why it has been found in some comets. But Roger Clark, who is based in Colorado, he found a method to retrieve the D2H ratio via infrared spectroscopy. So if you do the analysis of surface ice, you can derive the D2H in yes. So that's a real advance because it is the observations. And Roger Clark, he analyzed the value of the gas emission, and he found plenty of D2H value in the Saturn moons. You can see that in the name of the moons, in the rings also, in Enceladus also. That's very interesting. And we find those values which are all supersolar, they are all enriched compared with the sun. That's an indication to this supersolar value is very interesting. I need to tell you why. It allows us to distinguish two key scenarios of moon formation. Because if the CPD of Saturn was extremely warm, then the building blocks of the moon, the solids coming from the PSN, would have been vaporized within the disk before condensing again. Because there was vaporization and then condensation during the vapor phase, water would have exchanged its deuterium with hydrogen. This will have lowered the nuclear value in the gas phase, and once the water is condensed again, the D2H ratio should be much lower. This is the case because the value in the Saturn moons are cometary. It's like they were assembled from comets. So it means that the disk around Saturn was extremely cold. So that this indicates that a scenario is more likely than another for the Saturn's moon. Another point is also that the moons of Saturn, there are plenty of volatiles. So the examine Titan and also you see CO, CO2, N2, and so on. Argon, so this indicates the composition of Enceladus is like comet. It's a comet like after zero. There is another indication. This picture is interesting because there is here a bar for Callisto, which is it's a value taken from the whole Galileo data, and this value indicates that the D2H in Callisto is also supersolar because the solar value is there. So you see it's higher. So if this measurement is correct, this means also that Callisto at least form probably in a cold environment. So we have already hints about some information, but we need additional data from Clipper and just to have more knowledge. So what you see here it is different values. Observe the solar system. Recently, thanks to James Webb, values that we derived from Eris and Make, which are 2 big TIOs. And the D2H values have been measured in methane. It's easier to measure methane in infrared than it's easier to measure the D2H in methane than the D2H in water. So we are waiting for additional measurement in comets to compare those values. Anyway, let's go back to the meaning of measuring a D2H in the moon. What does it mean? Well, as I said, if the D2H in the moon is very high, that will indicate that the building blocks of the moon originate from the protosolar nebula. This is what we see here. So you have the D2H profile in the ice form of the protosolar nebula, and you see that there is a steep increase of the D2H value as a function of the distance to the sun. So ISM ice are really enriched in deuterium. It's maybe the enrichment is about 100 times the photosolar value. And so there is a gradient in the protosolar nebula because the disk, the inner region of the disk is very warm, so there is an isotopic exchange between water and hydrogen. And so what you see here is piloted by this reversible equation. And once the water freezes again, it frees the number acquired in the gas phase. But if you have a disk which is extremely warm, like the disk of Jupiter, what happened here is the fact that imagine you have icy grains coming from the PSN and entering the CPD. If the CPD is very warm, this isotopic exchange can be very efficient and it leads at the end to a protosolar value in the condensed water. So if the building blocks of the moon originate from the CPD, their D2H ratio should be protosolar. So measuring the D2H in the moons is a strong indicator of the origin of their building blocks.
So what variable is it most sensitive to? Temperature
And pressure.
Density or
Temperature, pressure. Temperature and pressure. And the efficiency of this chemical exchange is the best at above 400 K. So if you have a region of the disk which is at about 400 K, the isotopic exchange is very fast. That's the point. I show this figure just to show you a canonical scenario. So it is a work done with Sovarone, who did his PhD on the origin of the moons. This scenario is a classical. In this work, what we did here, we assume the moon formation from pebbles, and it is easy to form moons from pebbles in the CPD because when they migrate inwards, what happens? They lose easily their volatiles, so you can reproduce easily the density gradient between the moons. And this idea of migration inward and the volatilization due to the heating in the inner part of the disk is a classical idea which has been proposed since decades. We just revisited this idea with the pebbles. Why I say that? Because if you form your moon here, in the outer region of the CPD, the composition of pebbles is pristine. It comes from the protosolar nebula. If you form your moons here, the pebbles have devolatilized and they lose their volatiles. And thanks, based on those kind of scenarios, we can derive plenty of observational tests. Imagine we want to assess the origin of Europa thanks to the mass specs instrument which is located on europa-clipper. The mass specs instrument is a powerful mass spectrometer which is about the europa-clipper mission. And this instrument will be key to decipher the origin of Europa. So, three classical scenarios. Formation of the building blocks of Europa in a very warm CPD. Formation of the building blocks of Europa in a Babi CPD. I mean by that, they originate from the protostar nebula, but they have been progressively volatilized, and formation of Europa from pristine magnetism. Each of these three scenarios will lead to different outcomes, as you can see here. In a very warm disk, what happens? You have chemistry. So we know that the main bearing molecules in the PSM are, in the case of carbon, it is CO1, CO2. In the case of ammonia, or in the case of nitrogen, the main molecule in the PSM is N2. If we have a warm CPD, all these molecules will be converted into reduced molecules, CH4 and ammonia. So if you form moons in such environment, the dominating molecules, the building blocks of the moons, should be CH4 and ammonia. And of course, if you don't find those molecules, this will indicate that the moons form in a colder environment. So you can see that there are plenty of other tests. I will not detail them because it will take 2 hours. But you can make predictions for the D2H in various molecules, then 15 to 15, 40 to 15 ratio, and the abundance between double gas. So there is a grid of predictions we can use to assess the origin of the moons. So each scenario formation has a different outcome, and you can distinguish all these scenarios. That's the point I want to insist on. Let's shift to other things. Yes? In the exosphere. That is true. That's my concern also. So how can we assess that? I would say D2H, we will have multiple instruments. Mass spectrometers, infrared spectroscopy. So we'll be able to measure the exosphere, but also the surface. So we'll be able to see there is a fractionation between the surface and the exosphere. So that's already interesting. And there are also at the surface of Europa, there are regions which are fresher than others. So we can investigate the variation of D2H in the different regions of the surface. Because there is material coming from the inside, they upwell out, they go up, and there are fresher zones of Europa. So we'll see the difference between old regions and fresh regions. So that's it. So I think that I'm pretty confident for the D2H determination. About the noble gas, it's more complex.
So how many objects has the D2H ratio been determined differently, separately, through mass spectrometry and spectroscopy? How many objects? And do the two values agree? Because it is temperature dependent.
Yes, I would say yes. Actually, I think people working on that, they match well their data. So, in fact, it's
You
the case
want it
of
from a comet, right?
Yeah.
It'd be great to get it back from several comets.
that is true. Usually for comets, there are not multiple ways of measuring that because they are very distant. And there is just one.
Or, yeah.
In the case of 67P, pure emergency medical, the spacecraft was able to measure the heterogeneity at the surface, but it derived an average value. So it was interesting. But yes, but the paper by Roger Park was interesting to comment what you said.
So what were the variations?
Exactly. So if I go back to this plot, look at that. You can have an answer. Look at those data. The green value for Enceladus, the moon of Saturn, was derived from infrared data, and the red bar was derived by mass spectrometry data. You see there is a matching.
Yeah.
It's not bad. Huh?
No.
It's not bad. I agree. It's even better than many other measurements. For example, the oxygen determination in the comet. It has been measured by mass spectroscopy. It has been measured by in UV spectroscopy. There is no match. we understand nothing. So anyway, so I showed you those predictions. But let's go back to the origin of Jupiter and let's comment the consequences for the origin of the moon. So this picture comes from the Juno data. It shows the water abundance as a function of the ammonia abundance as measured by the microwave radiometer above Juno. It's a paper published in 20. I like this picture because it shows that it's a big mess. So let's consider the 2 sigma error bar. It is this contour. You see that there is a dependency between H2 and ammonia. You can see that the water abundance can be as high as 6 times the potential value of Jupiter, but can be as low as 0. And so that's what I mean by here. The water abundance in Jupiter is still poorly understood. There is currently a paper, I don't know if it is accepted or not, proposing that maybe Francis, you know that better than me, or Jonathan. There is a paper claiming that they get now a slightly supersolar abundance of water. So Scott Bolton told me that, but I don't know if it is accepted or not. It's a very recent work. Okay. So I'm still waiting for what it did, but I can tell you that it's very hard to measure water in Jupiter. I'm impressed by people working on exoplanets. They are stronger than planetary scientists. Because I see plenty of papers showing, yes, we measure water in HD something with tiny error bars. I'm very fascinated because in the solar system, we still don't know the water abundance in Jupiter, in Saturn, in Uranus, and Neptune. And at dozens of light years, you are able to do that. I'm impressed. You are brighter than us. I'm very bad, so I'm a planetary scientist. So, okay. Anyway, so in Jupiter, the water abundance is an open question. And one possibility is that there is no water in Jupiter. I don't believe that. But why not? Why not there is no water? Why? So what will happen in Jupiter for water flow? How can you explain water-free Jupiter if you have ice-rich moons around? Because the building blocks of the moon, they have the same origin as the building block of Jupiter. They should be formed in the same area. So you have a water-free planet. How can you explain water richness? It is a topic we try to address recently in my group, but let me, yes.
Yeah, just a brief comment, because I'm in Juno. So one of the issues we have is that we don't have polar coverage. And apparently water is quite more heterogeneous than we thought it was going to be. Now, by the end of the mission, the orbits are shifting, and we expect to have a little bit better coverage on the North Pole, so that can improve. Although it's still, as you mentioned, not understood.
And one is we sent the Galileo mission with the basic aim of the Galileo probe was to measure water. No, never been better than that. The basic idea of the probe, the Galileo probe, was to measure life in Jupiter. It is an idea from Carl Sagan. So you remember this paper from the early 70s. He was proposing the possibility of habitability in Jupiter. There are kind of animals in the atmosphere. So the idea of the Galileo probe, the mass spectrometer, was proposed by Carl Sagan himself. So of course, it was not powerful enough to measure life in Jupiter, but the basic idea was that. And when the Galileo probe was designed, it was the basic aim was to measure water. So it was not a success. As you know, the Galileo probe fell into a dry region in Jupiter, so the question was not answered. So the Juno mission was designed to measure water in Jupiter. And this is the result. You see, it's not Juno acquired plenty of nice results, but not this one. So it's still an open question. So I open a parenthesis. So Jupiter is rich in metals. There is a global enrichment in Jupiter, which has been measured by the Galileo probe. So to explain how Jupiter can acquire metals, we can use some ice plateismal models. So, for example, there are some ideas which have been proposed in the literature. It has been proposed, for example, that Jupiter had created amorphous platesimals. It was proposed by Toby Owen and colleagues in the end of the 90s. The basic idea is that Jupiter had created very cold platesimals. these platinums were coming from the ISL and remained freestyle. So that was the basic idea proposed by Tobiawan and Akiva Barnoun. Later, when I was a young kid, I worked on the idea that the platinums of Jupiter could be formed from plateaus. Do you know what is a plateau? Are you worried in the global warming on Earth? So you should know what is a plateau. You can write on Google plateau gun hypothesis. Yes, there are plenty of plateau on Earth. Plateau it's an icy structure made of it's a cage made of water molecules. In those cages, you can trap methane, CO2, powerful greenhouse gases. There are plenty of plateaus on the seafloor in the permafrost. Plenty of the sea. People working on glaciology, they analyze the composition of the air, which is stored in the carrot, and they found that at a given epoch of the Earth, there was a huge increase of CO2 in the atmosphere. And this huge increase, which appeared suddenly, is attributed to the release of greenhouse gases from plateaus. So yes, you should be worried. So because if they are unstable, they release the gas which is stored in the cages. Did you hear about the Bermuda Triangle? So I have a good news to tell you, it's not due to aliens. But there are some papers, science papers published in GRI proposing that it is the destabilization of plateaus in the Sargasso Sea, which allows the sinking of the boat. Okay, but okay, I go. So here, okay, so plateaus, there is a scenario which proposes that plateaus are part of the composition of comets. And why not of the building blocks of the giant planets also? When you accrete building blocks during the formation of Jupiter, there is a problem. So you form a gap around Jupiter, and because you form a gap, it's more difficult to accrete planetary zones because this gap created around the formation zone of Jupiter prevents the accretion of solids. A way to overcome this issue is to propose that the atmosphere of Jupiter, its metallicity, was acquired directly from the protosolar nebula. So there are several scenarios which propose how you can derive supersolar abundance of the protosolar nebula. So there was the idea proposed by Volga and Dech, 2015. So I released this work in 19. So the idea was to accrete gas released from the amorphous ice. If you come Jupiter here, you accrete supersolar vapors. And the other idea is the idea explored with Artem, in which we propose that we can have plenty of ice lines, one ice line per volatile. So the ice are pure condensates. And you can explain by doing so the composition of Jupiter, because you have supersolar gas within the protosolar nebula. So I don't mean that Jupiter formed by disk instability. I just mean it's possible that Jupiter accreted a supersolar model, whatever the scenario is, core accretion model or super disk instability model. We are consistent with those. Anyway, if you want to explain why the moons are ice rich and formed in a very dry environment, how can you do that? The scenario proposed earlier about the formation of moons from wet pebbles does not work. It's not possible. So what we explored here is the idea that the gay moons come from phyllosilicates, from hydrated minerals. Why? Because there was several recent work by Melwani, Daswani, and colleagues proposing that Europa could have accreted from such materials, minerals, and the 10% of water present in Europa is just a result of the outgassing of the derivatization of this material, which form the product from the hydrosphere of Europa. So, in fact, Europa, you can explain its volatile content via its accretion from hydrated minerals. By doing so, okay, you can explain Europa because the volatile fraction which is trapped in phyllosilicates is about 8 to 10%. You cannot explain Ganymede and Callisto, which are half made of water. It's not possible. So we need to find another scenario. So what we did here, we consider a classical disk model, CPD model of one Jupiter. We have the flux of pebbles called drifting coming in the disk. And here you have the location of the moons. Let's assume they form here. There are two interesting things. There is the phyllosilicate, the hydrogen line, and the solar line. What is it? The phyllosilicates, they lose their volatiles at around between 400 and 600 K at low pressure conditions. So if you have phyllosilicates, rich pebbles breathing through this line, they lose their volatiles. They lose their vapor, the water as vapor. What we have here is the first line of vapor. You increase, you form ice at this point. So any vapor going back to this region will freeze at this place. So what we have, in fact, we have phyllosilicates which go inward the CPD. They lose their volatiles, they lose their vapor. The vapor diffuse inward and outward, and the vapor diffusing outward is the game. So you have a source of ice at this location of the disk. And if you can explain Ganymed and Callisto at those locations. Okay, so I will not go into details, but I just show here that it's possible to explain the ice operation in the universe of the moon in a way consistent with their composition with this scenario. It's too wordy here. Okay. So there are several ways to test this scenario. The main test is to measure the D2H ratio, because in this scenario, the D2H ratio decreases with moving outward from Jupiter. The trend is at the opposite of what we could derive from the other scenarios. Yes, it's really the wrong slide, because I wanted to show you a view of the paper we published last week in Astronomy and Physics paper. It was we applied this scenario to the TRAPPIST system, and we showed that the density gradient of the planet could be explained by this scenario. So if you form the TRAPPIST planets with this density gradient, you explain. If you form the TRAPPIST planet with phyllosilicates, you explain the density gradient. It was a nice result, and it was advertised, but I lost it. It's my fault. Anyway, so I want to finish my presentation with this part. So I'm going to discuss with you about organic matter in the Protostar Nebula. Where did form organic matter? There are works actually which propose that organic matter formed in the ASM, in cold grain regions, irradiation or temperature effect on the cold grains transform some short molecules into organics. There are other experiments which show that you can form organics just with the UV flux in temperature range which are consistent with those in the Protostar Nebula. So, but there is still an open question: where the organic matter formed? Did it form in the ASM before the Protostar Nebula? Did it form in the Protostar Nebula? It's still an open question. And so what we so with Tom with the field, we investigated. We try to see where we can form the organic matter in the Protostar Nebula. So what we did, we used laboratory experiments. Laboratory experiments give you a temperature range of organic matter formation, and also an irradiation range of the UV flux which is needed to form this material. So we use this range of measurement. We use this experiment to assess where in the disk we can form such particles. So we use the PSL model, which derived from the work of Artem, and we use the Lagrangian scheme to track the particles. And what you get is there. So we can see here the motion of particles, which are released at different temperature, 20K and 80K. And we see their motion moving inward the disk. So there is vertical motion between terminals, and they move inward. And so what we find is that when particles are released at 20 K, it's possible to form organics. It's a PSN in the solar nebula. But when we release the particles at 20 K, it's not possible because they cross the X line of methanol before the time of forming organic matter. So if you want to accrete organic matter in the inner solar system, you need to form them far in the disk and at very low temperature to give them enough time to perform the irradiation of the particles. So it's a good news because you see that it's possible to form organic matter in the photosolar nebula. You don't need to form them in ISM. And I think I'm done with that. Normally, I should have shown you some different things, but it's my fault. So, okay, thank you very much for your attention. Thank you very much.
Thank you for the great talk, Olivier, and yeah, sorry that you couldn't show everything. But so now we have some time for questions, and maybe we can start with our early career folks.
If you think like what time they would make the most sense for all of these sonar interpreters, are we sure that they all form at the same time in the early sorts of sonar interpreters? Or are like maybe some of the ones that are like, you know, certain density between different times, the other ones at different times?
So yeah, there are several qualified people in the room, one behind you and another one before. So I can answer you, no, they did not form at the same time, at the same epoch. For example, we know that Callisto is purely differentiated, maybe not differentiated. Differentiation indicates the type scale formation. If there is no differentiation, it means that polygens were less energetic. So the accretion was slower. So maybe it takes 1 million years from a Callisto compared with Europa or IO, which are much faster.
Does that have to do with what you're talking about how when we migrate in, but once they form harmonic motions, they sort of like get settled in their orbits, which is what happened with the Galileans, because they're in the orbit. So that's what's going on with that.
It's a classical scenario. They are the embryos, they continue to grow during their migration, and they stop their migration when they are all in resonance with each other. It's a classical view, which since a few years, it applies well to the case of the TRAPPIST system and also the Aguichine systems.
When it comes to the formation of the company, you say we prescribe a review. Which kind of
Range. Is it indicated on my slide? I forgot. I have that in the paper, but I forgot the numbers. No, because I have the information in the paper, but it's based on an experiment by Tellerman and colleagues at PIL in Marseille. So we can use plenty of different experiments. So we put out this one, but now we are considering others which form nitrogen-rich organics. Because if you want to form Titan, you need nitrogen. So you need to accumulate nitrogen into Titan. So currently we are using other experiments which are more interesting to us. But yes, I can give you the number.
Waiting for Artem. Don't be fooled by the hubris of the exoplanet papers. I think when we don't know what we're doing and the systematic errors are dominating. This isn't the subject of your talk, but you did post a C to O ratio of 6 plus or minus 5 for Jupiter. Can you tell me a little bit more about what causes the large uncertainties in that value? Okay. I don't have the representative plot, but okay. So what it gives from the problem of Jupiter is it's already not homogeneous. So if you want to reach the bulk abundance, you need to go deep. So the only technique that ideally we should send an entry probe down to 1,000 bar. But we don't have the technology. So I think we are far away from this possibility.
The other technology is to use a microwave radiometer in orbit around Jupiter and to monitor the interior of Jupiter. So the microwave radiometer can go down to 100 or a little more bars, 100 bars typically. And the problem with this technology, with this method, you don't measure spectrum like in infrared, and what you do from the bed, you do high emission lights, so you try to fix them as best you can, and you derive a number. So what you get with the microwave radiometer, you have a continuum. You measure opacity. So you have an opacity continuum for water. The problem is that the opacity of water, this continuum is almost superimposed with that of ammonia. So you cannot distinguish the two. It's very difficult. So that's why there is this dependency between water and ammonia, because those two continuums are almost together. So that creates the huge uncertainty. There is no lines that you can match easier.
You showed, or you mentioned a very interesting result related to P670P, revising the DOH. Now, I know you're working on it and probably will be posting something, but can you comment on, I mean, this has huge implications, right, to the story of how volatiles are delivered to Earth, and in later years, it brings its favor that Jupiter family comets play a role, which means that planetary systems with a Jupiter-sized body maybe are not that of a signature of water. But I mean, this maybe is changing the picture. I know that there are other things like nitrogen that doesn't fit, and Earth.
Double gas also.
Right. Yeah. Xenon, I think it's the only thing that kind of works. And so do you think this revision of DOH has implications for this understanding of the role of the future?
Okay. I will just give you another hint. What are the differences? So it seems that during the evolution of the comet around the sun, there are some periods where the coma is fresher than that other period. So if you at some period, molecules diffusing from the comet are coming from, in some periods, they are coming from outer layers, in the other periods, they are coming from inner layers. And so the molecules coming from the inner layers of the comet are more fluid than those coming from the outer layers. That's why there is a difference between the DOH measured by Rosetta and the one we reanalyzed. Among all those data, we took those which were more representative of the blood composition. So that's okay. Anyway, so what will we learn with that? It's not the first time that we have a comet with Earth's DOH value. Artem also, it has been published in Science 1 decade ago. And the actual issue is that if it is a xenon isotopes in the comet, they are not the same as on Earth. It should indicate that the isotope of xenons 670P come from a different nucleosynthetic mix than in the case of the terrestrial planets. So it's in our solar reservoir. So it helps. Okay, of course, it's very attractive to see that the most known comet has a DOH which is like the Earth. It's very pretty. But the picture is complicated. It's still complicated.
So you seem to be saying that the comet is not reliable to determine DOH, and we should probably have a sort of surface sample return.
I don't say that. I don't say that the missing part of the puzzle. We have never sampled an asteroid, which is the asteroids are our closest neighbors, and it is likely that the Earth's building blocks were light those of asteroids. And we have never been able to retry directly there on the information. That's the missing piece of the puzzle. Sorry?
What was the question?
What about for you, the company?
Yeah.
You don't know.
Something?
So
Jupiter's very early luminosity is pretty uncertain. Is that an important luminosity here, or are there other uncertainties that dominate that, such that Jupiter's luminosity is just sort of noise?
It's well, no, it's not in the light, it's a key parameter. So if we took the parameter, we get different results. But that's important. So, that's why with this kind of models, it's easier to generalize the extra numbers. So, once you get the extra numbers, you know that the truth can be the middle between all the different numbers. There are plenty of parameters. Well, I was mentioning the turbulence. We all know that turbulence is a known mechanism.
Last short question or?
When you
Yes.
talk- Oh, when we talk about the molecular diversity, are we talking only on like the surface level of these moons, and are there any specific things that these like hydrocarbons are found on? Like highest concentration?
So we are talking here because we have also specialists of the moon, so don't hesitate to discuss with them, but I can answer you. The molecular diversity observed on the Galilean moons is very poor. So we are not that many, there are not many constraints. If you look to the Saturn moons, there is molecular diversity. So okay, we had cases highlights. So let's wait what will happen with those missions, europa-clipper and JUICE. But clearly, at present, we see molecular diversity at Enceladus in Titan. We don't see that in the Galilean moons. But I don't say they don't exist. Let's discuss again in 10 years.
Right, let's thank our speaker again.
Thank you.